The question says that two charges 5 into 10 to the power minus 8 coulomb and minus 3 into 10 to the power minus 8 coulomb are located 16 centimeters apart. At what points on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. Now we know that the notion of potential says that the electric potential V at a point P due to a charge Q at a distance R is given by V equals to 1 by 4 pi epsilon naught multiplied by Q by R. Here this is K, that is Coulomb's constant, and K times Q by R. Now the net potential energy due to multiple charges is the algebraic sum of the potential due to individual charges. So potential energy of a system of charge is just given by algebraic sum of individual potential on that point. For example, if Q1, Q2, Q3 are three charges and they are separated by a point P by the distance of R1, R2 and R3 respectively. So Vp or the potential due to this three system of charges at point P would be given by the algebraic sum of the individual potential. Now the question said that two charges Q1 and Q2 are there. Q1 is of positively charged, that is 5 into 10 to the power minus 8 coulomb, and Q2 is minus 3 into 10 to the power minus 8 coulomb. We have to find out the point between the line or the point on the line joining these two charges. So let us assume that there is a point P over which the potential due to these two charges is 0. Now as we have studied just now that potential due to a system of charges is the algebraic sum of the potential due to the individual charges. So we will find out potential at point P due to Q1 and Q2 and we will sum it and we will equal it to 0. Now solving this equation we will find out the value of x. Now by the value of x we will get the point at which the potential due to charge Q1 and Q2 equals to 0. Now similarly proceeding with that strategy, we see that potential due to charge Q1 would be equal to KQ1 divided by x and potential due to charge Q2 would be equal to KQ2 by 16 minus x, because if this is x then the total distance is 16 centimeter, then this distance would be 16 minus x or 0.16 meter minus x. Now proceeding with the calculation we will get the value of x as 10 centimeter, that is 10 centimeter away from point Q1 the potential due to these two charges would be equal to 0. Now there would be another case where the point may lie outside these two charges on the same line. So let us take the second case as like this. Q1 and Q2 are here, they both are 16 centimeter apart, and let us assume that point x, the point P at a distance x away from the Q1 charge on the side of Q1 charge. Now proceeding similarly like before, we will get the equation. Now after solving this we will get the value of x to be minus 0.4 meter. Now minus suggests that, so since we have taken this distance as our desired assumption that the potential at this side would be 0, now we have got the value of x as 0.4 minus 0.4. so minus suggests that this point lies on the other side of the charge and by 40 centimeter away from this point Q1. So 40 centimeter away from Q1 on the right side would be somewhere here. Now 40 minus 16 centimeter would be 24 centimeters. So 24 centimeter away from charge Q2 or 40 centimeter away from charge Q1 on the right side. Thank you. The question says that a regular hexagon of side 10 centimeter has a charge of 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. Now the system of charge here is a hexagonal pattern. Now on each vertex of the hexagon there is a 5 microcoulomb charge present, and we have to find out what is the potential at the center of the hexagon. From the previous exercise we also know that potential at a point P, which is at a distance r from the charge Q, is given by Vp equals to K Q by R, where Q is the magnitude of the charge and R is the distance of separation between the point of our interest and the charge, and K is the Coulomb's constant. Now for the system of charges, this potential is just the algebraic sum of the contribution of individual charges to the potential, because potential is a scalar quantity. Now for this system of charge, that is a hexagon pattern, we will have to find out potential at the center. Each side of hexagon makes 60 degree as a center, which makes it an equilateral triangle. Now for the equilateral triangle each side is same, that is each side of hexagon is 0.1 meter, so the distance of center from the vertex would also be equal to 0.1 meter. Now, finding out potential of the system, we can write it as Vp equals to summation of kqi by ri, where I varies from 1 to 6 because there are 6 charges, and that would be, since the distance of separation is same, so we can simply write it as 6 times k q by r, where q is the charge on the vertex and r is the distance of separation between the vertex and the center. Now that will give us a value of 2.7 into 10 to the power 6 volts. Thank you. The question says that two charges 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. Identify an equipotential surface of the system and what is the direction of electric field at every point on this surface. Now we know that electric potential is defined at a distance r from the charge q as kq by r. Now here a term used is equipotential surface. So equipotential surface is a surface on which electric potential remains constant. No work is done in moving a charge along this equipotential surface. The system of charge is given as there are 2 points A and B, that is 6 centimeter apart, and on A there is a positive charge of 2 microcoulomb and on B there is a negative charge of 2 microcoulomb. We have to find out equipotential surface of this charge configuration. So let us proceed by general approach. Electric potential at any point P would be given by kqa by r1 plus kqb by r2. Now here qb is negative of q1, so we can write it as 2 into 10 to the power minus 6 by r1 minus 2 into 10 to the power minus 6 by r2 whole multiplied by k. Now for Vp to be constant, that is potential to be constant, r1 and r2 along the path should be constant. Now we know that the locus of a point equidistance from two fixed points is always a straight line representing perpendicular bisector of the segment joining the given point. That is, the locus of point that is equidistance from these 2 points should be this perpendicular bisector between these 2 points. Now the equipotential surface would be a plane located between the charges at a distance of 3 centimeter from each charge. The electric field at every point on the equipotential surface is directed perpendicular to the surface, pointing from positive charge of 2 microcoulomb to negative charge of minus 2 microcoulomb. Thank you. The question says that a spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 to the power minus 7 coulomb distributed uniformly on its surface. What is the electric field? Inside the sphere, just outside the sphere, and at the point 18 centimeter from the center of the sphere. So here in this question, a sphere is given which is a conductor and it has a radius of 12 centimeter and it has a charge of 1.6 into 10 to the power minus 7 coulomb distributed over its surface. Now we have to find out electric field in 3 different areas. The first is inside the sphere, and the second is just outside the sphere, and third is at a point 18 centimeter away from the center of the sphere. Now we know for a property of conductor that any excess charge inside the conductor resides on the surface of the conductor. No net charge is present inside the conductor. So for the first part of the question that said that what is the electric field inside the sphere, we can apply Gauss law. Inside the sphere, assuming that there is a Gaussian surface inside the sphere, there would be no charge inside the Gaussian surface. Thus, flux would be 0 because there would be no charge inside the Gaussian surface. Thus, electric field would be 0. So, for the answer of first part of the question, that what is the electric field inside the sphere, the electric field inside the sphere is going to be 0. The second part of the question says that what is the electric field just outside the sphere. So, for this, we can assume that for a point outside the conductor of radius 0.12 meter, we can consider all the charges Q to be present at the center. Now by Gauss law, we can say that phi net or the flux net through the Gaussian surface would be equal to Q enclosed divided by epsilon naught. Now Q enclosed is the charge enclosed by the Gaussian surface. Now flux is defined as the dot product of electric field and the area. Now area of the sphere, surface area of the sphere would be equal to 4 pi r square, and E is the electric field. Now here we are assuming the whole sphere to be the Gaussian surface. So the charge on the sphere would be Q enclosed, and area would be 4 pi r square, because we are assuming the surface sphere as the Gaussian surface. Now E would be equal to 1 by 4 pi epsilon naught multiplied by q by r square, where r is the radius of the sphere. While calculating, we will come to the conclusion that electric field just outside the sphere would be equal to 10 raised to the power 5 Newton per Coulomb. Now the third question said that what is the electric field at point 18 centimeter from the center of the sphere. Now in this case, we can assume that entire charge is concentrated at the center, and thus we can take Gaussian surface to be a sphere of radius 18 centimeter, and thus, like previously, we can calculate electric field like using this formula, and we will come to the conclusion that electric field is 4.4 into 10 to the power 4 Newton per Coulomb. Now in this question, one of the most important thing that we applied as a property of conductor was the net charge on the conductor resides on the surface of the conductor, not inside the volume. Thank you. The question says that a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. What will be the capacitance if the distance between the plate is reduced by half and space between them is filled with a substance of dielectric constant 6? So we know that a capacitor is a device that is used to hold charge, and capacitance is the ability of the component or circuit to collect and store energy in the form of electrical charge. Now capacitance of a parallel plate capacitor is defined by C equals to epsilon naught A by D. So here we see that there are geometrical components in the formula of capacitance, that is A and D, which is A is the surface area and D is the distance separating the plates, and the capacitance with the dielectric material between the plates is given by K times C naught, and K is the dielectric constant. So the first question said that what will be the capacitance if the distance between the plate is reduced by half. Now it is saying that if the distance between these two plates of a capacitor is half, then what would be the capacitance? So if distance between the plate is half from, let us assume that earlier it was D and now it is D by 2. The capacitance, which was earlier C naught, would be changed to CF. We have assumed that the new value of capacitance would be CF. Now C naught, that is earlier capacitor, when the distance of separation was D, the formula would be epsilon naught A by D, and now since it is half, it would be equal to epsilon naught A by D by 2. Now we can see here that CF would be equal to 2 C naught, that is capacitance will increase if the distance between these two plates is halved. Now the second part of the question said that, and the space between them is filled with the substance of dielectric constant 6. Now the space between these two plates is now fixed with dielectric constant of 6, a substance which is having dielectric constant of 6. So we know that the formula for capacitance with the dielectric constant is given by K times C naught, that is K is a dielectric constant. So we can say that since the dielectric constant of that material is 6, so the final capacitance would be 6 times C naught. So the final capacitance when the distance between the plate is halved and the space between them is filled with the dielectric material of constant K equals to 6 would be equal to 2 times 6 times C naught, which will be given by 12 times the previous value, that is 8 picofarad that was given. So the final capacitance would be equal to 96 picofarad. Thank you. The question says that 3 capacitors, each of capacitance 9 picofarad, are connected in series. What is the total capacitance of the combination? And the second question is, what is the potential difference across each capacitor if the combination is connected to a supply of 120 volt? Now we are here given 3 capacitors which are connected in series, and we have to tell what is the total capacitance of the system, and in the second question we have to find out what is the potential difference across each capacitor. So one of the most important property of a capacitor is that when capacitors are connected in series, then each capacitor connected has equal amount of charge. That is, when they are connected in series like this, then if this capacitor has charge Q plus Q and minus Q, then each of this capacitor will have same charge. So the first question asked about C equivalent or total capacitance of the combination. Now the C equivalent for series combination is given by the summation of reciprocal of each capacitor. So 1 by C equivalent equal to summation of each capacitor 1 by C, where C is the capacitance of each capacitor. Now as per the given question, each capacitor is of capacitance 9 picofarad, so the total capacitance would be equal to 3 picofarad as per the calculation. Now the second question asked about the potential difference between each of this capacitor. Now each capacitor is connected in series over here, and we have to find out what is the potential difference across this one, that is V1, V2 and V3. So potential difference across each capacitor is given by V equal to Q by C, that is charge contained by that capacitor divided by the capacitance. Now we have already discussed earlier that charge carried by each capacitor would be same, and it is given by C times V. Now calculation of C times V will give us a charge of 360 picofarad. That is 360 picofarad of charge is available on all the capacitors. Now calculating voltage for the same would be V equal to Q by C, that will give us 40 volt. So each capacitor will have 40 volt across, the potential difference across each capacitor would be of 40 volts. Thank you. The question says that 3 capacitors of capacitance 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel. What is the total capacitance of the combination? And the second question is, determine charge on each capacitor if the combination is connected to a 100 volt supply. Now the parallel connection is like this. The question is saying that there are 3 capacitors. We have named it as C1, C2 and C3. They are connected in parallel. Parallel connection means they all are receiving the same voltage or same potential difference as that of the source. So there are certain properties that are worth noting when capacitors are connected in parallel. The capacitors that are connected in parallel has the same potential difference across each other as that of the source. So each capacitor here, C1, C2 and C3 will have a potential difference across each other of 100 volts. Now the second property is that they store charge independently of each other, in contrast with that of in series connection where each capacitor stored equal amount of charge. Now the first question asks that what is the total capacitance of the combination. Now so the C equivalent in this case should be 2 plus 3 plus 4 picofarad, that would be equal to 9 picofarad. And the second question says that what is the charge on each capacitor. So charge on capacitor is given by Q equals to C multiplied by V, where C is the capacitance and V is the potential difference. Now each is having the same potential difference of 100 volts, and the capacitance varies as given, that is of 2, 3 and 4 picofarad respectively. Now similarly we can use this formula C multiplied by V to find out the charge in each capacitor, and we will get as 200 picofarad, 300 picofarad and 400 picofarad. Thank you. The question says that in a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 to the power minus 3 meter square, and the distance between the plate is 3 millimeter. Calculate the capacitance of the capacitor. If the capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? Before attempting this question, we should have our concepts clear about capacitance, that capacitance is a measure of capacitor's ability to store charge per unit voltage. For a parallel plate capacitor, the formula for capacitance is epsilon naught A times D, where A is the area of plate of the capacitor and D is the distance of separation between them. Now the question said that calculate the capacitance of the capacitor, and the second question was if this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor. So once we know the formula for capacitance, we can easily calculate it, because epsilon naught here for air is given by 8.85 into 10 to the power 12 minus 12 farad per meter, and A is given, that is area of the plates, and D is also given, that is the separation between the plates. Area is 6 into 10 to the power minus 3 meter square, and D is 3 millimeter, or it is 3 into 10 to the power minus 3 meter. Now substituting these values, we will get a value of 17.7 picofarad for the capacitance. And for the charge on capacitor, given the potential difference, we know its expression is C times V, or capacitance times voltage. Now capacitance is 17.7 and voltage given is 100 volt. So its result would be 1.77 nanocoulomb. Thank you. The question says that explain what would happen if in the capacitor given in exercise 2.8, that is the previous exercise, a 3 mm thick mica sheet of dielectric constant 6 were inserted between the plates while the voltage supply remained connected, and the second case is after the supply was disconnected. So here two cases has been given, and the event that is occurring is the capacitor previously calculated of capacitance 18 picofarad and the charge accumulated on that capacitor was 1.8 nanocoulomb. Now this capacitor is being subjected to two conditions. The first is while the potential difference is maintained or external supply is there to maintain the potential difference across this capacitor, a dielectric material of constant 6 is being inserted. Now we have to find out what will happen. And the second case is the dielectric material is being inserted while the voltage source or the potential difference is not being maintained. That is the case 2. So in the first case, the capacitance will change, and the capacitance with dielectric constant is given as C equals to K times C naught, where K is the dielectric constant and C naught is the capacitance in vacuum. So previously calculated value was the capacitance in vacuum, that is of 18 picofarad. So new capacitance would be equal to 6 times 18 picofarad, that is 108 picofarad. Now since voltage maintained of 100 volt, so it will not change. The capacitance has changed to 108 picofarad. So the charge accumulated will also change because C has changed and V has remained constant, and charge is given by C times V. So the new charge contained would be equal to 10.8 nanocoulomb. So we see here that while the potential difference was maintained, the capacitance has increased and also charge storage has increased because there is a source available for charge. Now the second case was the dielectric material was being inserted while the potential difference was not being maintained. So in this case, we can see that Q before the dielectric material was being inserted, and after the dielectric material has been inserted, the charge on the capacitor will remain same. So the potential difference is given by Q by C, and this capacitance has increased because we know that C is given by K times C naught. So the voltage would be equal to, voltage across the capacitor would be equal to 16.67 volt. So in this case, we see that capacitance has increased just like before, but voltage has decreased because charge has remained constant. And in the previous case, this was not the case. In the previous case, there was a charge sink and source available. That's why the charge rearrangement took place. While in this case, there was no any sink or source of the charge. That's why the potential difference dropped while Q remains same. Thank you. The question says that a 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? Now in this circuit, there is a battery and there is a capacitor, and this is the battery and this is the capacitor, and the capacitance of the capacitor is 12 picofarad and the voltage of battery is 50 volt. Now we have to tell how much electrostatic energy is stored in the capacitor. The electrostatic energy stored in the capacitor is given by the formula half CV square. C is the capacitance and V is the voltage across the capacitor. So upon using this formula with the given data, we can calculate the electrostatic energy stored in the capacitor, and that would be equal to 1.5 into 10 to the power minus 8 joule. Thank you. The question says that a 60 picofarad capacitor is charged by a 200 voltage supply. If then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor, how much electrostatic energy is lost in the process? The case is, once the capacitor of 600 picofarad capacitance is charged by a 200 volt supply, now it is the battery or the voltage source is disconnected, and in place of that source there is another capacitor, uncharged capacitor of 600 picofarad is implemented in the circuit. Now the circuit becomes like this in a series. It is asking that how much electrostatic potential energy is lost in the process. So we have to calculate electrostatic potential energy in the first case and the second case, and now we have to find out the difference between both. Now potential energy or the electrostatic energy is given by half CV square. Now initial electrostatic potential energy would be equal to half 600 picofarad multiplied by 200 volt square. Now that would give us 12 microjoule. Now after the capacitor is removed with the battery or the voltage source, and connected to another uncharged capacitor, the total charge on both the capacitor is going to be same. Charge in case 1 and charge in case 2 is going to be same. Now charge rearrangement will take place, and thus since the capacitor in second case is connected in series, so we will get the equivalent capacitance as C1 plus C2, and that would give us 1200 picofarad, and voltage across the capacitor would be equal to Q by C equivalent. Now Q, we know that Q is going to be same because there is no any supply to pump extra charge, so Q would be equal to C1 V1, where C1 and V1 are the initial capacitance of the circuit, and the voltage divided by C equivalent, that is C equivalent becomes 1200 picofarad, so we will get the voltage as 100 volt. Now the final energy after connection is going to be equal to half C equivalent multiplied by final voltage square. Now that would give us 6 microjoule. Initial energy was 12 microjoule and final energy we have got as 6 microjoule. So there is a difference of 6 microjoule, or 6 microjoule is lost in the process. Thank you.